also one thing though, whenever your tank keeps freezing up, then you have to use your computer and your computer don't go to sleep.
True, my computer's not going to go to sleep. That's for sure. Okay. Especially considering I definitely don't have 30 minutes left of lesson. It takes 30 minutes before my computer goes to sleep, so. Okay. I believe I've talked about example 4. If f of x equals e to the x times x squared plus 1 raised to 100th, what is f prime of x? Okay, thoughts on this problem? Based on the fact that I mentioned the product and quotient rule, what do you notice here? Yeah, we have a product rule going on here. That little dotted line is my way kind of saying, hey, you know, there's my product rule because I've got e to the x, which that's its own function, right? And I've got x squared plus 1 to the 100th, which is a function. So we have to do a product rule. So remember product rule, derivative of one of them, or we usually say derivative of the first, keep the other, plus, and then it's derivative of the second, keep the first. However you guys say it at this point in your careers, your math careers. So in this case, we're going to use a product rule. So derivative of e to the x. E to the x times the x squared plus 1 to the 100th as is. And then what? Product rule has a plus. And now we reverse the situation. So this time, last time it was derivative of e to the x, keep the second part. This time we're going to keep the first part, so we're going to keep the e to the x, derivative of x squared plus 1 to the 100th. Okay, so, yeah, similar to what we just did before, where it's something raised to the 100th. So that's going to be 100 times the something raised to the 99. What's the one more detail? Times the derivative of x squared plus 1, which is 2x. So there we had product rule and chain rule within the product rule. Okay, definitely gets a little more confusing. You have to be careful there. Now, let's see. I'm trying to figure out, and you guys did note this here, that the 2x is because we did derivative of x squared plus 1. Let's see. In terms of cleanup, got two different options for you. One option is to just kind of keep the two separate, the first part and the last part, to just kind of do some cleanup on the last part. So e to the x times x squared plus 1 to the 100th pretty much stays as is. If we clean up this second part to make it look a little nicer, the 100 and the 2x can multiply. 100 times 2x is going to be 200x times e to the x times x squared plus 1 to the 99th. And to be honest, that's probably the answer that you would see in most places. However, we're going to try one other thing. We're going to get kind of fancy here. As it is right now, can you agree that we have two big terms? Okay, so we have this e to the x, x squared plus 1 to the 100th, and we have this 200x e to the x, x squared plus 1 to the 99th. We can factor out a GCF here. Actually, we can factor out a couple of GCFs. What GCFs do these two terms have in common? Okay. They both have an e to the x. They both have x squared plus 1. How many x squared plus 1s do they have in common? And they both have 99, yes? This one's going to have 1 left over here. And so, a way we can write this is we can factor out those GCFs. So, e to the x is a GCF. And x squared plus 1 to the 99th, because that's all that's in common. Okay, so those are GCFs, if that helps there. As we look at the first term, we're taking out the e to the x, we're taking out x squared plus 1 to the 99th. What remains? X squared plus 1 to the first if you want, but I don't need to write that first, so that's just an x squared plus 1 plus the second part of this. So if we take out e to the x and x squared plus 1 to the 99, what remains? 200x. Oops, 200, about lost my x. What did you say? Wish they could. And I guess if it was really buggy, you could clean it up instead and say x squared plus 200x plus 1. But with everything else we have going on, I don't care about that. Okay, you ready? One last one. Can't get my page turned here. Huh?
I said I'm scared.
You're scared you want to go home? So are you catching the feel that this one looks kind of big? Well, here's what my old notes look like for those of you in class, that you can kind of see it. I mean, I actually managed to get mine in before we hit the line. I just have 3 big rows of work. Okay, so as we look at this one, f of t equals sine of t plus natural log of t all over t cubed plus 3t to the 5th. What do you have to remember to do here? Yeah. You've got to think quotient rule and chain rule. And when we talk chain rule, we're going to talk the chain rule, twice, I think, within this problem. Okay, so I will start over here. F prime of t equals. There's my help. Okay, how's my quotient rule go? Remind me.
You take the top term derivative by the bottom term, then you take the bottom term derivative by the top term, and you square the bottom term and then the bottom.
Okay. And the one thing that Daryl did mention, so he said derivative of the top, keep the bottom term. Then he said derivative of the bottom, keep the top term. What sign goes in between there? It's a minus, yes? Product rule is plus, quotient rule is minus. So, derivative of the top. Here we go. Derivative of sine of 2t. Okay, so the derivative of sine of something is cosine of something. Derivative of that something. So what's derivative of 2t? 2. So if you guys don't mind, I'm going to go ahead and say 2 cosine 2t. Plus, okay, we're still doing derivative. Derivative of natural log of t. 1 over t. And officially you can say then times the derivative of t, but derivative of t is just 1. So that is my derivative of the numerator times what? The denominator, so t cubed plus 3t to the 5th. So that's derivative of the top times the denominator. And then I'm going to say minus, now what? Derivative of the bottom. So derivative of that something to the 5th. Okay, 5 something to the 4th. So 5 times t cubed plus 3t to the 4th. And before you move on, we have to say times the derivative of that something, which is derivative of t cubed plus 3t. 3t squared plus 3. Okay, so that's the derivative of the denominator times the numerator as is. So sine 2t plus natural log of t. Zooming out, zooming out. There we go. Now I'm all on the screen. And this is going to be all over. Okay, t to the 3rd plus 3t to the 5th and squared. But when you square a power that's being raised, when you square something, you're doing a power times power. So yes, 5 times 2 does make it to the 10th. Okay, in all honesty, that could be an answer. Okay, there really is not a ton of cleanup that can be done, but there is some cleanup. And so we are going to look at some of this. One thing I would suggest you look at, if you think about there being 3 big terms in this problem. On top, it's one term minus another term. In the bottom, there's a term. What do you notice about all 3 terms? They all have what? Okay, they all have a t to the 3rd plus 3t to some power, yes? How many, if you start looking at those, t to the 3rd plus 3t to the 5th, t to the 3rd plus 3t to the 4th, t to the 3rd plus 3t to the 10th. How many do they all have in common? They all have at least 4. That means there are essentially t to the 3rd plus 3t to the 4th, that 4 of them that can cancel out of every single one of them. It's like, if they all divide by 2 and we divide them all by 2. They all will divide by t to the 3rd plus 3t to the 4th. So in that one, it's just gone. In the first one, if it's raised to the 5th and we divide 4 of them away, now it's going to be a power of 1. Huh? Okay. And the denominator, if there was 10 and we divide 4 of them away, that leaves me with 6. So those are kind of my new powers there. Okay. As we look at this first term up here, what do you notice about t cubed plus 3t? There's a GCF of t. Now, I'll be honest. It's not as important in my other ones, but, I forget, do I usually look at it? I do, okay. In this one, that t is going to be important because, I'll tell you right now, a fraction within a fraction is not a very friendly answer. Not that this is a friendly answer, but, so if we factor that t out there, from t cubed plus 3t, that means I'm going to put a t out front, and then I'm still going to have left in parentheses t squared plus 3. And we still have the other parentheses that I don't want to leave behind. 2 cosine 2t plus 1 over t. Minus. On this next set, we don't have any GCF, so there's not really anything to clean up. Oh wait, never mind, we do have a GCF. What GCF is obviously there? There is a GCF of 3. So we already have a 5. I can factor out GCF of 3 from that next parenthesis, leaving what in the parenthesis? We factor out 3, we still have t squared plus 1. And then I still have times sine of 2t plus natural log of t. All over. It's t cubed plus 3t to the 6th. Do we have a GCF here? We have a t, and when we take a GCF of t out, it's going to be t to the what? 6th. So I can write this as a t to the 6th times t squared plus 3 to the 6th. Okay, I think there's only a slight bit of cleanup here, like 5 times 3, which you guys probably already multiplied. But here's the one thing I can do. I have a fraction that's 1 over t, yes? What does it take to get rid of a denominator of t? Multiply by t. What did we happen to have as a GCF here? A t. So this t it multiplies by one parenthesis or the other. Well, I already factored out this parenthesis. I can distribute this t to both terms in this parenthesis, and the advantage of doing that is I will no longer have a fraction within a fraction. So, final answer that I'm going to leave it as. I'm still going to have t cubed plus 3, t squared plus 3. I'm going to distribute a t into the next parenthesis, which makes it 2t cosine of 2t plus, what about 1 over t times t? Becomes a 1. Minus 5 times 3 makes it 15 times t squared plus 1 times sine of 2t plus natural log of t. All over t to the 6th times t to the square plus 3 to the 6th. That's how I have my final answer written. Obviously, this is a situation where there are lots of options. Part of what I'm doing here is just trying to show you some of the options of what happens when you start messing with these big things. Okay? Questions there? Okay.